In this video, I'll talk about logical equivalence. So the way math is written is you start with some definitions, which it's not clear where the definitions come from, but these are written in retrospect. Then you write some theorems using those definitions, and you finally prove them. This is the standard structure for every single math book. And this is what we have done so far. We have done a lot of definitions, and now it is time to do some theorems. So we will today do our first theorem, which is called the De Morgan's law. Also, a caveat, that's not how math is discovered. Discovery of math is much more nonlinear and very creative and fuzzy. All right, so that being said, before I come to the De Morgan's law, I need one more definition, and that definition is of logical equivalence. You can think of this as equality in logic. So what is logical equivalence? Two statements are logically equivalent if they have the same truth values. All right, so this is like equality, as I said, and you already know one example, one very basic example, that is P and not P. So not P flips true to false and false to true, and if I were to do it twice, then I'll flip it back. And so I'll say that P is logically equivalent, or P and not P are logically equivalent. And this is written symbolically as P, and then instead of equal, we have three horizontal lines. Equi is equivalent to not P. Okay, so that's the new definition. And logical equivalence is very, very important. In math, we are often trying to determine if two statements are saying the same thing. And this is making that formula. So we come to our first theorem, that is the De Morgan's law. De Morgan's laws are logical equivalences for negations. What they say is not of P and Q is logically equivalent to not P or not Q, and not of P or Q is logically equivalent to not P and not Q. So what is happening is that when you have negation, the and becomes or, and the or becomes and you can push the negation inside the brackets. How do you prove logical equivalence? The only way to prove logical equivalence is by building truth tables. I'll only prove the first proposition, and I'll just build a truth table for both the left-hand side and the right-hand side. Now here, the components are just P, Q, and also I have P and Q, not P, not Q. So it'll be there will be a lot of columns, and I'll just have to fill in one by one. So that's all I'm going to do now, silently. Now not P must be the opposite of what's in the column of P, so that will become FFTT. Similarly for Q. Or no, P and Q is ANDing the first two columns. So I'll get. And then not P and Q is negating that. And finally, not P or not Q is, let me highlight these, is taking the OR of these two columns. And as you can see, these two columns are exactly the same. And so this proves that not P and Q is logically equivalent to not P or not Q. And similarly, you can prove the other De Morgan law by building the truth table for the other equation. And I encourage you to do it. It's very easy. Just follow exactly this method. So that's how you prove equivalence, just by building truth tables. And we have done our first theorem and proof. So yay. We're going to do one more theorem and proof of logical equivalence. And that is something involving something we saw yesterday, namely the converse, the contrapositive, and the inverse. Just quickly recall that if you have a statement P implies Q, then the converse is obtained by flipping the hypothesis and the assumption, the hypothesis and the conclusion. So that will become Q implies P. Contrapositive is obtained by flipping and then making them negatives. So not Q implies not P. And the inverse is, you don't have to remember, but it's not P implies not Q. Okay, so now what I'm going to do is I'm going to patiently build the truth table for P implies Q and the converse and the contrapositive, and you'll see what's happening. Now here, the statements, the propositions I need are P and Q, and not P and not Q. So that's it. Maybe I'll just copy these from the previous truth table. All right, that was convenient. So now I'll build P implies Q, Q implies P, and not Q implies not P. Now remember that in implies the only time something is false is when the assumption, the hypothesis is true, but the conclusion is false. So I'm looking for when P is true, but Q is false, and that happens in the second row. So this is the only time I'll get false. Now let's look at Q implies P. So now here the hypothesis is Q. So I want Q to be true and P to be false. And that happens in the third row. And now for not Q implies not P, I'm looking for not Q to be true. So not Q is true in second and fourth, but not P is false in the second. So I'll get false here, and the rest are all true. And now let's look at the columns carefully. If you look at the fifth column and the seventh column, then what you'll see is that these two are exactly the same. On the other hand, here we have a discrepancy. They are not exactly the same for the fifth and sixth column. And hence we have shown that a statement is logically equivalent to its contrapositive. But not to its converse. And I'll give you an exercise. See what happens for the inverse. Here also you will see something very interesting. And this statement, this theorem that we have just proven is very, very, very important. We use the contrapositive a lot. In fact, in the next chapter, we will see proof by contrapositive. And I kind of want to give an example in words to see that this is not that surprising. It's just that this simple fact is extremely useful. So let's do an example. Let's do a mathy example. So let's say, so let x be a real number. Then I can form a statement. If x is greater than 2, then x is greater than 1. This statement is true. If something is greater than 2, then it's also greater than 1. Now, what will be the converse of this? So in the converse, I just flip the hypothesis and the assumption and the conclusion. So it will become if x is greater than 1, then x is greater than 2. This is clearly not always true because you have 1.5 which lies between 1 and 2, and so this is false. On the other hand, if I were to make a counterpositive of this, then I have to negate both the hypothesis and the assumption further. So I'll get if x is less than equal to 1, then x is less than equal to 2. And if something is less than equal to 1, then it is also less than equal to 2. And hence this is true. And so you can see that so what we are actually saying is that these two statements, which look kind of different, are actually logically equivalent to each other. And yeah, so now we have our first theorems in logic.